So what should we do? If Bruce says a few words and then is silent and does a few noddies.
Yes, you can see what it looks like. If I give you, I'll put the link into the chat. And there we are, it's now running.
So what should we do? If Bruce says a few words and then is silent and does a few noddies.
Yes, you can see what it looks like. If I give you, I'll put the link into the chat. And there we are, it's now running. So yes, you can see what it looks like.
Let's see if there's enough bandwidth in Chiddingfold for that to work.
You should be able to see the YouTube.
Yep, I can see it.
Probably me concentrating. Oh, Cara's there now. Much nicer.
Okay, so welcome everybody to this RTS presentation on PTP. And we still don't have my head.
There's about 30-second or minute delay, I think.
Okay. Oh, there we go. Yes, remember to look at camera, Bruce. There we go. Welcome everybody to this RTS presentation on PTP. And we still don't have my head. All right, well, that's doing my head in with a 30-second delay, so I'll get rid of that. Okay. Oh, there we go. Yes, remember to look at camera, Bruce. There we go. Excellent. So somebody's got the sound unmuted, which will, again, confuse us all. Make certain everything's muted, folks, especially the YouTube feed. All right, well, that's doing my head in with a 30-second delay, so I'll get rid of that. Okay.
Let's go to Gerard, shall we now?
Oh, there we go. Yes, remember to look at camera, Bruce. There we go.
Yep. Okay. Well, so let's talk a bit about PTPs, one of my favorite subjects. Thank you very much. Is that enough head nodding?
They're looking for a stunt double for the Churchill dog, so if you could carry on for another minute or two.
Thank you.
Anytime.
Careers advice too. Awesome.
There's no end to my talents. Oh, no, sorry,
Yeah.
my talents have ended. Sorry, I get that wrong all the time. Sorry, my talents have ended. Sorry, I get that wrong all the time.
Can we just get Richard? If Richard could speak and then nod to camera.
Hi there.
So you've got 3 minutes to go. So just confirm, Simon, obviously the YouTube is running now to record.
Yep, you should be able to see that. It's recording.
59, we just mute all those of us that are not taking part and we'll disappear.
And I'll switch on at 59:30.
And Mark, it's over to you, love, at 1700.
Yep.
Break a leg, as us lovies say.
Once I hand over to Bruce, I'll quit my video, and that should make you center the stage, I guess.
Yeah.
What might be a good idea, Mark, is when we get to 59 seconds and I switch it on, you just say something to take the camera, and then everyone else be quiet so that you're the one that shows for that period.
Okay.
Yeah. Right, 1 minute and a quarter.
During the panel discussions, Mark, if it looks like that I've become a verbose narcissist, feel free to interrupt. Somebody's got their hands up, because there's a high likelihood that might happen.
1 minute.
Right, enjoy yourselves. I'm going to disappear now.
Thanks, Tim.
Be worth muting whoever's making noises. Was that you, Mark? No, it was
Nope.
Tim. We're on Tim. Can you say something, Mark,
Yep, speaking 1 2 1 2.
to take the camera?
Okay, still speaking, still speaking, still speaking.
Okay, you have it.
Fantastic. 30
5
seconds.
Going off now.
Yep. Good old time.is. Fantastic. Hello and welcome to this RTS Thames Valley Technology Centre seminar. We're here tonight to listen to 3 fantastic speakers talking about the challenges and implementation of Precision Time Protocol, PTP, within their environment. We first have we have Dr. Richard Hopcroft, has a long interest in time and founded his company in 2010 with the original intention of supplying smart mechanical watch movements. Time has moved on, however, and he will explain the concept of traceable time as a service and share some ideas how this might be relevant to television. We also have Gerard Phillips, no stranger to the RTS Thames Valley, those who came last in 2019 to Simply 2110 lecture. Gerard is system engineer with Arista Networks who can share with us some of the best practice implementations and what lessons have been learned along the way. First, though, we start with Bruce Devlin, who is Standards Vice President at the Society of Motion Picture Television Engineers, or SIMTE to be short. Bruce has a vast experience in this area and will give an intro in the 2110 toolset and explain why time is so important in the broadcast domain. However, before I hand over to Bruce, I'd just like to point out, if you have any questions, please post them in the chat, or indeed put your hand up and hopefully we can connect you into the discussion. May I now welcome Bruce to guide us through this session, and please do join in with your comments and questions at the end. Thank you.
And thank you very much, Mark. And welcome everybody. What an outstanding audience for a rainy afternoon here in the UK. I've just left a Zoom meeting where people were showing the beautiful sunshine streaming down on Los Angeles and some of the mountain views in Denver with the snow on the ground. So go British rain is all I can say. We love you. So I'm going to kick off. I'm going to spend probably somewhere between 5 and 10 minutes just telling you a little bit about some of the interesting things that we have to do to bring PTP into a modern broadcasting environment. And like all good things that are broadcasting, there's a bunch of legacy that we always have to take into account. So I'm just going to talk a little bit about some of those things, and then I'm going to hand over to Richard, who'll tell us a little bit about some novel and interesting ways of looking at PTP. And then Gerard will open Pandora's box and rummage around inside there and tell us some of the wonderful things you actually have to do to make all this stuff work. And as Mark said, if you do have questions, please raise your hand and ask them verbally. Any of you who know me know that my reading skills are somewhat limited, and my multitasking skills are even more limited than that. So please raise your hand and we'll try and get you to ask a verbal question. So, a brief history of time with our new funky SIMTE logo. So I'm a great believer in understanding why things are the way they are and what it is that we tried to carry with us into the modern era from the previous era, because that helps you really form some of the, some of the rules about how we have to use modern systems in the context of backwards compatibility. And particularly in broadcasting, we've never had a clean slate. Once we start doing something in one way, it's very difficult to just start with a brand new clean field site and do something absolutely brand new and different. Although Nowadays, we're doing a very good job of that by inventing HDR and PTP and IP transport. We're doing our very best to throw off the shackles of the past and to be modern and flexible and agile, but some things you just have to carry with you. So I thought I'd just throw up a slide, and I hope you can see my mouse waggling around here, otherwise just try and imagine it, to have a look at what we were doing in the analog world, the sort of the pre-1980s world, and then what we kind of did in the SDI world, which was up until about 4 or 5 years ago, and then what we do in the IP world, and really what are some of the nails that we put into the corner of these particular standards and specifications in order to make what we've done in the past carry through to what we need to do today. So those of you who played with analog video will remember the joys of trying to cram, oh, that should have said Hank, apologies for that, first typo, straight there on the first slide. We had to cram all sorts of metadata and control signals and other stuff into various bits of the picture signal, because really the picture signal was the highest bandwidth thing we were trying to cram through. And everything that we were sending around a TV plant was video line raster based. We jammed all of this strange data, audio metadata and control signals around the edges of the picture. But fundamentally, this analog thing that we were putting down coaxial cables was a self-clocked and self-timed signal. And to get everything to time and sync up, you had to cut your cables nice and accurately so that any two routes would arrive at the endpoint to the analog switcher at the right time. We had a master clock, probably somewhere in the facility, that was putting out some sort of regular metronomic heartbeat to try and keep both your black and white and your colored in signals all working nicely. And it was really flying by the seat of your pants. There was no storage, there was no rebuffering, there was no reclocking. And the delay between the photons going into the front end of the camera and then hitting the eyeballs of the viewer was measured in probably microseconds. So it was really live, really hard real time. And actually, timing errors were very visible to everyone instantly. So digitizing all of that lot, really we kept the whole concept of the raster with us. And over time, we ended up having effectively the frame-based heartbeat carrying on the piece of cable. The piece of cable, for various compatibility reasons, was very often still a bit of coax, but it might have been a fiber over an SFP. We jammed different rasters into that timing interval, but by and large, we were still a frame-based timing interval with a raster on it to jam all the metadata in there as best you can. It was still a point-to-point unidirectional network. It was still self-clocked and self-timed, and we still had this master metronome kicking around somewhere in the building to try and keep everything together. And then all of a sudden, we've gone to this packet-based world where everything's a packet. Whatever it is, you put it in a packet, and if it's not the same thing as another thing, you put it in a different packet and label it differently. And that's really quite a fundamental sea change to everything that we've done in the past. Clocking actually depends on the link type. And the timing of all of those packets really depends on having some external master clock that's some huge orchestrator trying to pull the whole thing together. And all the routing was packet-based, so it didn't really matter whether you were point-to-point or star configuration. The packets could flow independently of the way that you put all the wiring together. Really quite bottom-clenchingly terrifying compared to, the good old analog days. So if we think about some of the constraints of putting all of this thing together, what we were trying to do is we needed to somehow synchronize all of our frames together. We need to synchronize fields together. Ooh, interlace, sorry, I thought I'd got over that, but still interlace causes me the heebie-jeebies. We had to get all the lines synchronized, especially if you were working in frame rate standards conversion in live and semi-live environments. We had to get color subcarriers synchronized. We had to get your 8-phase PAL sequence synchronized. There were all sorts of weird things that had to be synchronized, including pixels and audio samples. So we had things like master clock generators, and we had daily jam workflows, which were an elegant solution to an inelegant problem. Or is it the other way around? I don't know. Maybe you can comment later in the comments. We had drop frames and non-drop frames to try and count all of these various synchronization modes that were floating around anachronistically into our networks. And remember, we were going from an environment where buffering was really hard. Low latency was really easy. Hard real time is what we had. And everything everywhere had the same timing. to the extent where there were all sorts of interesting synchronization systems for all the transmitters up and down the country, were all beautifully synchronized to each other for terrestrial TV. Then if you compare that to where we're trying to go to, buffering's really easy. Latency is evil, which makes low latency hard. So actually we're in a completely different operational paradigm now. Hard real time actually becomes quite hard because buffering's easy. People tend to put buffers all over the place. I remember being on a music shoot once upon a time where nobody'd realized that there was a 1-frame delay in every one of the monitors. Now I'm pretty much tone deaf, so I couldn't spot that, but all the musicians couldn't figure out where these extra milliseconds of delay were coming from. It was the monitors we were looking at. Really terrifying where you find buffering nowadays. And actually, because everything's so flexible, we live in a world where actually the intra-timing within your facility probably needs to be really, really strict. But as you move between facilities, there are financial and operational constraints that might mean that making that timing constraint a little bit more floppy might be economically attractive to you. And depending on the sort of program you're putting together, the more floppy might be better because it's cheaper or better or something. So we're going into a world where the economic drivers for timing are very, very, very different to the way that they were just 3 or 4 years ago. And we've seen specifically in this new COVID era in which we're living, where we've got live audiences via Zoom or YouTube, seeing things that might be seconds delayed compared to what's happening live in the studio. Now, with my standard of jokes, it's quite often for me to tell a joke and people not to laugh for a day or two. But when you're trying to put together a comedy program, that actually might be quite tricky. So there's, depending on the genre and the nature of your program, it can be quite interesting how you tie all of this timing together and what sort of timing requirements you might have for a program. I've already mentioned accurate timing when you need it and floppy timing between the two. So we're now going to dive into some of the specifics. Now I've kind of set the scene of, we've got operational flexibility or chaos. We've got easy buffering, but hard low latency. And somehow we have to tie all of this together with preferably, hopefully, one single glorious standard that's going to make it all work. So I'm now going to hand over to Richard. I'm going to stop sharing my screen. And Richard is going to talk to us about the miracle that is PTP and some of his extremely interesting views on how we might want to push it around the world to make the world better. Richard, over to you.
Okay, can you see my screen?
Certainly can.
Okay, jolly good. So perspective I come from is that we've been distributing time in other industries originally. We started in 2015 when the financial services industry recognized it had a problem. Essentially, the problem was initiated with an event on, I think it was the 10th of May 2010, about 2:30 in the afternoon, New York time. A load of automated trading systems suddenly started going crazy and starting trading at floor and roof prices. So for several minutes, Accenture share price was 1 cent per share, and for a glorious few seconds, Sotheby's was valued at $6 trillion. So that was a bit of an embarrassment for the banks involved, that things could go so wild. But it was a far bigger problem for the regulators, because what happened was when you went back and looked at all the records of what happened, all these banks were trading with clocks that slightly differed. So you couldn't actually work out who did what when. And so nobody has ever come to the bottom of the cause of that event. The result of that was the MiFID regulations in the European Union and the consolidated audit trail in the United States in order to ensure that banks made sure that their transactions were correctly timestamped so that you could identify causality, you know, what happened first and what could have triggered what. So their need is a little different to broadcast because they need to know the sequence of events rather than any kind of synchronization. But when we first got into the business, we thought we would be selling lots of clocks, software, helping banks actually synchronize. But what we discovered was that banks actually have lots of places where they have a small number of servers because their servers need to be co-located with the exchanges so they can do high frequency transactions. So it was going to be very, very difficult to supply them time by installing clocks locally. The cost would be massive. So what we developed, and this is probably our biggest USP, is the fact that we over time mastered the idea of actually distributing time as a service. So rather than having equipment on site that was providing time, actually networking time itself, just in the same way as ST2110 uses IP for distribution of the media content. We were doing the same with time as a service. Now that seems to work, so I'll go into details of the level of accuracy we can achieve and so on. But if we just think for a moment about to compare and contrast the requirements of SMPTE 2110, you don't actually care about causality. What you do need is synchronization between different sources and make sure they're aligned. But in a similar way, low cost is always a driver. So in any way that we can reduce equipment costs, reduce capital expenditure and swap it over to operational expenditure, that's always interesting. And the timing requirements are rather similar. So for MiFID II financial regulation, for example, the granularity needs to be down to 1 microsecond. And our high frequency trader has to timestamp to UTC to about 100 microseconds. So we're talking the same sort of ballpark. So what we did in terms of establishing a time distribution network was actually to look at time delivery from the core, what we call the stratum 0 sources. So in terms of satellite distribution, we lock into the Galileo, GPS, GLONASS, Beidou satellite systems. We've got 5 timing hubs around the world, 2 in New York, 2 in London, 1 in Tokyo. And then in order to have some resilience against satellite failure, we've also got a landline from the RISE Standards Institute in Sweden. And these timing networks all reference each other, and then in a sort of hub and spoke network, then deliver time out to where our customers need it. So what are the challenges we came across? And these are challenges that you would see not just in the finance industry, but also in the broadcast industry. The first is that people are increasingly moving to the cloud. And if you go to Amazon and ask to put an antenna on their roof, you won't get a very nice answer. And although they do have some kind of time services, they're not particularly accurate, and they certainly don't provide any support level agreements on them. So timing in the cloud particularly needs some kind of time delivery mechanism that's wired. Second issue is that you can't always put up an antenna even if you're you're renting your own space, because the landlord may not let you. You may be in an outside broadcast situation where you're stuck in an underground car park, that kind of thing. There is a growing concern about GPS vulnerabilities. maybe this is more for critical national infrastructure, but it's becoming increasingly common for jamming and spoofing of GPS, which is a very weak signal, to occur. Most notoriously, a GPS system will never work wherever Vladimir Putin is. And so you'll find that, for example, early last year, our ex-President Trump passed an executive order. That's nice to say, ex-president, isn't it? Okay, passed an executive order which actually said that all critical infrastructure should actually have some other alternative to satellite distribution for position, navigation, and timing. So that threat has been recognized. And finally, it's very important that this is plug and play. It's from my work with broadcast engineers, the IP is clearly something new, and it's not something we want to give you lots of options on. We just want to say, if you do it simply and do it like this, it'll work. End of story. So that is something that's come back to me very clearly working with broadcast engineers, that simplicity is king. And equally, resilience is king. So as I've learnt in my learning curve on IP distribution for media, there's two of everything. So in this particular model, there's an orange network and a blue network, and both will function completely independently. And we should probably be extending that to the time sources. So maybe there are multiple time sources, some of which are terrestrial like ours, some of which are satellites, so that we've always got the best, but we've also got something as an alternative that we can rely on. So why do we need synchronization in IP media? Well, previously we had SDI, which, as Bruce said, has its own timing built in. We're sending video content and audio content over IP is asynchronous. So there's no guarantee when it will arrive. We might have a packet collision and it'll take a little bit longer to arrive. So something needs to resynchronize all these packets when they arrive from all their different sources. So this is the fundamental reason why the ST 2059-2 requirement exists, is so that we can align time as it's sent over IP media. So just building a little bit more on what Bruce was saying about accurate time and floppy time, if we look at the two kind of areas of regulation, or sorry, not regulation, but standards, which have been developed for media. First is ST 2015-2, which is what happens in the sort of like accurate time environment, which is within a facility. And there you need some kind of island of time that can achieve 1 microsecond accuracy. And then between facilities, we've got the sort of floppy time that Bruce was talking about. And there, the Joint Task Force on Network Media actually initially specified 100 milliseconds accuracy between facilities. But in reality, the time quality does need to be better than that. So we say the absolute minimum standard should be 1 millisecond, and ideally at least an order of magnitude better than that. The reasons this becomes important is because of things like if you've got two TV screens in a pub and they're transmitting at different times, it becomes very noticeable. If there are financial repercussions to what's being transmitted, such as you're doing online gambling or transmitting news which people will trade on, we do need much, much tighter time. So this is why we set the limit of 1 millisecond, and ideally factor of 10 better than that, 100 microseconds for the entire delivery chain. So some of the tests we've done, working with Arista, we did some work early last year, delivering time. What we did was we delivered it over some of our financial networks. We sent the time Amsterdam, Frankfurt, Paris, and back to London again, and then had it land on an Arista switch, which would then regulate the time down to the 1 microsecond that the island needs. We did that on what's called layer 2, OSI layer 2 distribution, and we could achieve that to 1 microsecond. OSI layer 2 is kind of the distribution that high frequency traders use. So it's very, very good, but quite complex to set up and expensive. So then we sent it over the sort of standard telco extranets that they have for private financial work. And we were getting 10 microseconds with those, but certainly a hell of a lot more flexibility. Particularly one of the companies we work with quite closely is BT. We are well aware that they work in the broadcast industry as well. And finally, some tests we ran last month, December, we actually looked for a completely plug and play solution, something that could be set up from outside broadcast or something like that. And then we used what we call a VPN IPsec tunnel, and we did it from these same 5 clocks you see photographed here to an outside broadcast research facility just outside Chelmsford. And there we were achieving time distribution accuracies of around 30 to 40 microseconds. So in terms of achieving the time distribution to the between facilities requirement, that worked well. And then what we use is some kind of boundary clock at the receiving station, such as a switch or a Grandmaster clock, to actually make sure the synchronization within the island was to the SMPTE requirement of 1 microsecond. So that's just graphing those different layers of achievement. And it works quite well. It's very reliable. Particularly the one we favor is the VPN type design. The reason for that is it's very plug and play. Our experience now with outside broadcast truck people is that they want something very, very plug and play. They don't want to be messing around with IP networks too much. So that seems to be the sweet spot that we're looking at. So just to compare the different media, well, traditionally over SDI, there would have been a local synchronization developed, potentially synchronized over GPS, and then that would be used to generate pulses on a SPG, and that would then go and synchronize all of the contribution feeds, the production, and the play out. As we move on to IP media and ST2110, there's still the traditional GPS kind of synchronization route. And what we're saying is that that should be supported by a land-based terrestrial route, which once it gets down to the switch IP layer, will synchronize an island at a time and allow the synchronization to actually work on traditional media as well as the new SMPTE 2110 way of doing things. Just to wrap up, we feel that what we've done in financial services is equally compelling here, because I think the biggest argument is the low hassle, because nobody really wants time synchronization. Nobody apart from me wants time synchronization to be their biggest problem. They don't, it's a problem they want to go away and just plug and play and have it done. It's also important to try and reduce costs and reduce the costs you do have to operational, if you can, rather than capital expenditure. And as when it's combined with satellites, the terrestrial time gives you that resilience and security that makes you, that guarantees that whatever happens, you'll still be able to get the program out on time, because otherwise there's no point in transmitting real-time load. And this is something we've been doing for a while now. So we've managed to prove that it works, and we think it'll work in the IP media arena as well. Okay, thank you very much.
Outstanding. Thank you, Richard. Fascinating and totally different. So right, we're now going to switch over to Gerard Phillips, who's from Arista, and he's going to be telling us some of the hands-on dirty things you need to do to actually make this work. So Gerard, over to you. I should say clean hands things, really. This is all the modern world.
Yeah, have I managed to share my screen properly there, Bruce?
Yep. Well, I can see it.
Magic. Okay, super. So thank you very much. Thank you, Richard. That was fascinating stuff. And I think it really is, as 2110 continues to gain a lot of mind share, then this idea of being able to synchronize local islands and then to interchange the content between those islands is obviously going to become just more and more important. There was a question about the kind of latencies and interconnecting between Japan and Australia in the chat. I was going to say that there has been some really interesting work done by NEP Australia on that. They did a bunch of live remote production from Japan back to Australia using their Andrews Hub technology. So I guess it's a mind change from thinking that everybody has to be perfectly synchronized, and this is the point that Richard, I think, is making, and Bruce with his floppy time. There's always going to be latencies between, there's time required to get the transport of 2110 or whatever compressed flows you're looking at between these locations anyway. So having the time being perfectly synchronized between those two remote locations doesn't make any sense to me, because you're going to have to accommodate 10, 20, 30, hundreds of milliseconds at the other end anyway. So this is really good stuff. So what I wanted to talk about today was zooming into those little into the local broadcast center. I'm going to talk about 2110 itself, how it works, and some of the lessons that we've learnt as we've built systems for people building 2110. Hopefully that'll give everyone a feeling for what I really want to do is make sure that people can walk away from this feeling like PTP is not the evil, difficult protocol that it's kind of getting a little bit of a, it's being characterized as being difficult. I don't think it is difficult, it's complex, but actually there's some relatively simple rules and some architectures and some templates. That's, I guess, what I want to put across here. Templates. If we do things simply and repeatably, that gets us to the point where this stuff is, we can roll it out more effectively and more efficiently to kind of, irrespective of whether it's a large or a small installation. So 2110 is built, it's a profile built on top of 1588 PTP version 2. It's worth saying that it is really, really widely used. So industry automation, financial trading, as we've already talked about, power generation. I mean, how do you think all those moving power station, all those generators are synchronized? It's through PTP. It's already used for mobile backhaul, synchronizing the data there. CERN uses a special version of PTP to timestamp its particle events. In the media world itself, of course, AVB, Dante Ravenna, AES67 have been using PTP for many, many years. And it's going to become more and more and more common. 5G requires an awful lot of synchronization at the base stations to interleave the frequencies and make make your mobile phones work. Tons and tons of IoT will be everywhere using PTP to synchronize stuff. And believe it or not, there's a massive push for PTP to be available on the desktop. Now, what for, I have absolutely no idea, but there is this in the next few years, we'll all have PTP available to our desktop. Now, how accurate will that be? I don't know. What profile will it use? I don't know. My point is there's going to be tons of this stuff, and there already is tons of this stuff. So let me give you a quick whistle-stop tour of how does PTP work. I mean, the challenge we've got with PTP is we're looking for high accuracy, tens of nanoseconds maybe, in a boundary clocked system. We're looking for high accuracy in an environment where we've got fundamentally asynchronous transport, and where these little important packets are possibly being pushed out of the way by big video packets and even jumbo packets of other sorts. So there's the potential for an awful lot of ambiguity about the amount of time it takes to get from one place to another on a packet by packet basis. So the magic is pretty simple, actually. You've got some sort of, I'm sorry about the master and slave notation on this slide. I didn't have time to fix this one, but the clock, the grandmaster sends out the time. It looks at its watch and says, "Oh, it's 3:10, and it sends that message to everybody. And it does that in takes about, it does eight a second. So 8 times a second, it tells everybody what the time is. So 8 times a second, all the endpoints will receive that time and understand what time it was when the grandmaster sent that time. That's brilliant, but we don't know how long it took. Could be 1 microsecond, could be 200 microseconds, no idea. And so what happens is the endpoints, the followers, will periodically, 8 times a second as well, it turns out, send back a message called a delay request back to the grandmaster. And the grandmaster will timestamp that and send that data back in a delay response. So if you look on the slide, you've got T1, T2, T3, and T4. So these are the timestamps at which the data was sent. And all of these timestamps are essentially sent to the follower, the endpoints. And there's a simple set of differential maths on the right-hand side. You can make it as complex as you like, including filtering and median filtering and all sorts of filtering that you fancy doing to try and get rid of outliers and stuff. But what you end up with is the ability to create two simple outputs from these 4 timestamps. You can understand the delay between the network delay between the grandmaster and the endpoint, and you can therefore do some more maths and calculate the offset between the endpoint and the grandmaster. Once you've got the offset, you can correct that offset, right? So this is reliant on a few things. It's reliant on the forward and reverse path being synchronous, and it's reliant on those network delays not changing very much. But if you have those in a well-designed network, then you can have very, very accurate time. Sounds perfect, but there are places where these errors creep in. The network is going to be made up of multiple network devices, switches, routers. What does a switch and a router do? It's got buffers, it's got synchronization, it's got it has to multiplex data packets from one place to another. As those packets are multiplexed, they get buffered. This is where the buffering comes in that Bruce was talking about. As they get buffered, then the delay through the switch changes. So the simplistic view of the maths suddenly falls apart a little bit, in the sense that you're adding in unknown jitter to the path between the grandmaster and endpoints. So the math starts to fall apart. All the places with the red arrows, those are potential jitter injection spots. There's nothing you can do about it. It's what switches do. That's how they do their magic. So what we're going to end up with is packets and timestamps that have got this inherent jitter built into them. So what we need to do to create accurate time is to get rid of that jitter. And what we have is a time-aware, PTP-aware network. We've got 2 methods we can achieve this with. There's a transparent clock and there's a boundary clock. And they're subtly different. They achieve the same thing in different ways. Boundary clocks, essentially, the switch will create a local copy of the upstream clock. It becomes a follower, creates an accurate version of the clock, and it then serves that everywhere else. So because the traffic doesn't go through the switch, there is no jitter, because what you're measuring and locking to point-to-point links, it's very accurate. There's a few other advantages from boundary clocks. You can tie in their network scalability and security, and the ability to change the messaging rates if that's what you want to do. So that's a preferred way of achieving good accuracy. Transparent clocks is the other method, and this is simpler if you like. The time taken to transit the switch for each packet is accurately identified and incorporated into the message, and that means the endpoint can accurately reconstruct the real time that packet took. So 2 easy ways to make your network PTP aware. And if you build your networks with this sort of technology, you can genuinely get to plus or minus 10, 20, 30 nanoseconds at the endpoint. So incredible levels of accuracy. Need to touch on resilience and simplicity, reliability. There's a lot of confusion about how to build PTP. Really, there's some simple templates, and here I'm sharing the simple template. Really, a couple of grandmasters, a couple of switches potentially to distribute the time between those two. Give yourself some resilience. If you lose a GM or one source of time, then you've got another source of time, which is what Richard was mentioning. Fundamentally, multiple connectivities between the places you need them. Flow the time down the screen. In this case, makes it a lot easier to understand quite what you're doing. And if you build boundary clocks everywhere, it makes life a bit simpler. You can build in security with mechanisms that prevent ports from being able to be led by other parts of the network. You can lock ports to only the ports you want to be lockable to the GMs can be lockable to the GMs. The boundary clocks are very scalable. So if you have hundreds of endpoints, if you're boundary clocking at each level, then the endpoint, the leaf layer of your leaf and spine is still probably only looking at 40 or 50 endpoints rather than having to deal with maybe 1,000. So you're offloading the scale from the grandmaster, for example. Flexibility, as I said, you can change the messaging rates in a boundary clock. So there's a very simple template. We all know that broadcasters love to reinvent, do things differently because they've got a special thing they need to achieve. Actually, with PTP, it's way simpler if we just try and stamp out this template each time, really. There's a lot to get through, and I just want to cover the importance of visibility and monitoring. PTP is kind of like one of the most fundamental parts of your network. If your timing isn't working, things aren't working. Endpoints will overflow, buffers won't work, glitches will happen, audio won't be synchronized, left and right won't be there, clean cuts and things like that won't occur. So it's well worth remembering to include the visibility and monitoring of your PTP subsystem. There are many tools that will enable you to do that for the grandmasters and for the endpoints. A good PTP aware network will also give you a ton of data about the status of the network from the telemetry of the network switches, in terms of its understanding of the grandmasters that are available, the status of those grandmasters, the number of endpoints following the clocks, deviations from offset from master, which is essentially clock errors, deviations in the network delays. This is all data that's available out of switches to help you be comfortable that your PTP subsystem is operating correctly. I don't want this to be an eye chart, but it's just a couple of examples of the sort of visibility you can get. So down at the bottom, we have logging of changing of grandmasters. So every time you have a failure, you want to know what's causing that. You want to know that you've gone to another good master. Measurements of the performance of the network. This is an enormous mean path delay. That's because it's a Raspberry Pi in my garage rather than something half decent. Numbers of messages on the interface, on the ports. This is a brilliant way of debugging stuff at a very low level. So hopefully you won't need to get to this stuff, but the data is all there. There's a ton of visibility available in good PTP aware switches. So kind of concluding, I don't want to take everybody's time unnecessarily. I try to kind of coordinate a bunch of lessons learned. So PTP is not inherently secure, but there are tools within the boundary clock way of operating which allows you to build security in. You can create ports that are defined as being master only ports, leader only ports, so that they can only provide clocks. They can't be ports through which the switch will lock to another grandmaster. So, you know, you should only really have 2 ports in your entire network that are host facing, that aren't in the mode of being locked, and those would be your 2 GMs, right? Take a lot of care when you come to non-2110 audio. Dante, Ravenna, those guys often use PTP version 1, which is essentially deprecated in the rest of the IT industry. So both of those standards, I believe, will operate quite happily with PTP version 2 if you have the right software versions and you enable it. So that would be a massive learning pain point from the interops I've been to. Cutting corners with non-PTP switches is painful. So trying to connect into other networks where they aren't inherently already PTP aware, think very carefully about that. Maybe a little bit of extra cash would make that pain go away. Try not to mix transparent and boundary clocks if you can. Our recommendation would be boundary clocks everywhere you can. Design for resilience. I mentioned it already, it's really important. Losing a GM is not too bad. Losing 2 GMs is not too bad. The network will carry on going. The switches will hold over, but time will drift. We don't have accurate clocks for holdover. And when you come back to a good clock, when the GM is brought back online, that's going to be a big kick. So get to the point where you never lose a GM. Don't lose both GMs, rather. And then there's a concept in PTP and 2059 of management messages, which allow special TLVs to be sent around. They are often the cause of a lot of pain. So test your system with the management messages enabled, and then disable them if you're not using them. So to summarize, PTP is essential. It is complicated, but honestly, it's not voodoo and it's not rocket science. Build a monitoring system as a first-class citizen. Get good input from all of the vendors you're interested in. Do a proof of concept with those guys. Make sure you build in enough time in your schedule for the testing. And yeah, did I mention the monitoring? Make sure you do some of that. So with that, back to you, Bruce, I think.
Thank you very much, Gerard. 2 extraordinarily good presentations. So we're going to go into a bit of a panel session now. I've got some of my own questions, but I thought just before we dive into that, I'd just ask Mark if he could unmute Pryn Boone for a second, because I want to do a slightly little shameless plug for some of the work that's going on in SMPTE, where, as Gerard said, monitoring's good. Knowing what you're monitoring's better, and knowing how what you're monitoring relates to the network is betterer still. So Pryn, please could you tell us a little bit about some of the work going on in SMPTE in that area?
So, well, thanks for the ad hoc invite, Bruce, and hey, Richard, hey, Gerard. So yeah, Gerard, thanks for the plug. That's a perfect segue. So as part of the work and the input from Gerard and other people in the industry, we kind of identified that unlike in the financial services world, where you've got these highly managed systems and you've got these small, very closely knit services, very tightly bound to the dark pools that are working in broadcast, we have lots of manufacturers and lots of endpoints. Gerard mentioned potentially thousands of them in the system, all of which will have different capabilities and from a range of manufacturers. And in our inimicable way in the industry, we all tend to do it individually based on our own companies and our own practice and everything else. And that's fine. We've worked with that. Now, within the spirit of sort of IT cooperation, some work was undertaken by the ICF, which resulted in a RFC called 8575, where they produced a thing called a YANG data model. So some more funny jargon. YANG stands for yet another next generation brackets data modeling language, which basically was an attempt to document all the parameters related to version 2 of i50-1588 that which is based on what the SMPTE profile uses in a structured way. It's the idea is that everybody uses the same data set, the same syntax, and the same ranges of numbers are applied. And it's a common dictionary, if you like, that you can send it via smoke signals if you wish, or by net. By CLI or whatever you want to do, but you're sending the same names and everything else. So at SMPTE, we've taken that work with Bruce's blessing and working on a draft recommended practice, which is called 2059-15. So we've taken that Yang data model, also with the in conjunction partly with the work of the IEEE, who've extended it as an experimental model for the 2019 draft. We've taken that and also added on blocks for GPS monitoring, also for status of grandmasters, and also taking into account some of the parameters that may help to understand about GPS spoofing. So there's that model is available on GitHub. So it's SMPTE/RP 2059-15 if you want to search for it for comment. There's a questionnaire on there as well about has this got the right number of parameters, and some of the fine detail in there. So that's available for comment in the industry. Please, if you've got the time and you're interested, take a look on there. We're very interested in your feedback. And the output from this will go into our RP, and then this will eventually go into to feed into the IEEE work, who are working on their own Yang data model and also MIB for PTP. But that will take 2 or 3 years. So there's an IEEE PAR, as they call it, for the work program that's ongoing. So in terms of monitoring, absolutely, there's a lot of work going on behind the scenes for monitoring. And please, if you're interested, get involved. And there are both with ourselves and also with the IEEE. Thank you.
Thank you very much, Pryn. And all that documentation and the questionnaire and everything is freely available on the SMPTE website. Yes, that's it, free, unusual for SMPTE, but we're trying our best to get as much inclusivity as possible. So we really do need your help in answering some of these questions. So we've got about 10 minutes to go to ask some questions. There's been a few good ones. I'm actually going to kick off with the one that, Gerard, you mentioned that people have been doing a bit of testing, but I'm going to fire it at Richard because we haven't heard him speak for a little while. How do you build an outside broadcast where you've got Australia, Japan, the UK, and I don't know, somewhere difficult, let's call it Antarctica? How do you actually do that when, well, it's difficult? Richard?
Well, interestingly, in financial services, we're currently just putting in a link between Tokyo and Sydney for low latency synchronization. Yes, the distances are large. We have found Asia by far the most problematic place to achieve synchronization because the undersea cable networks are somewhat chaotic and very long distance. But for the floppy time, it's good enough, but it's the least good. So we're probably looking at sort of like 50 microsecond synchronization between Tokyo and Sydney. Now that's synchronization. Obviously, the latency itself is quite a lot larger than that. So that's our experience. We haven't actually done anything in broadcast down to Sydney yet, or to Tokyo.
And Gerard, given that that's the timing accuracy you can achieve, in practice, does anybody actually see that? I mean, compared to the sorts of interesting problems you get going up to satellites and back, even double hop satellites, presumably it's less traumatic?
But I think sorry.
So I was trying to mix the effects of latency and the effects of timing synchronization accuracy. So even if you've got synchronization accuracy, that's the massive 50 milliseconds that Richard was talking about, presumably microseconds, sorry, my brain's going dead. Presumably that causes fewer problems for you than some of the more extreme delays that we get in the industry, or does it? But what actually happens?
Yeah, so I think I mean the two things are different, right? They're two different challenges. The need for accurate time at both ends of the link is in order to be frequency locked, right? Not phase locked and not latency locked. So you want a good clock at both ends so that your audio, your stereo is still stereo, your 5.1 is still 5.1, and the lip sync is still good, right? So given that you may have 200 milliseconds between two locations, actually what is more important is a good, stable, same frequency, not a perfectly accurate within 5 nanoseconds phase, because that's lost the moment you send it across your 200 millisecond link. So the challenge really is about workflows, and it's about how are you going to mix those videos when they arrive? How are you going to offset those videos? How are you going to have local content mixed in a way that the local talent can see or use as local feedback? So mostly it's a workflow problem where you end up with potentially with in the case of Andrew's hub in Australia, they have all of their bulk video processing is in Australia, and what they backhaul is the content, but they provide locally mixed audio, for example, for the local talent monitors, such that there's no latency. That is now the proxy of the Australian mix. So they have a local proxy of the Australian mix so that the talent still understands what's happening and doesn't have the half a second latency. But all of the problems we've always had in this industry of synchronizing lines in and dealing with lines out, they're all still there, right? Physics hasn't changed. So having everything nicely synchronized is great, but those problems clearly haven't gone away.
So that's a lovely statement. I may steal that from you. Physics hasn't changed despite the recent 4 years of American government. And on that front, there's a question about VPNs from Jonathan. He says that when testing over the VPN, how did you manage to ensure a symmetrical path? Does that make a difference? And did you manage to do it? And does that affect physics?
It doesn't affect physics. It's more the other way around. So we can't guarantee a symmetrical path, but the asymmetries we see when we do measurements where we've got high accuracy clocks at each end, if we just do a naive VPN, it would be fairly significant, well into the tens of microseconds. If we do it in a way that's well understood, with a lot of control over the network providers, then we can get it right down to about 10, 20 microseconds. So when we've done VPNs over private extranets, where we can dictate to the telcos exactly how they route it, then we get very good results. Over the public internet, there's the other reason we use VPNs, which is, in our experience, a lot of ISPs will actually block a lot of UDP traffic, PTP traffic. So unless you do actually encapsulate it, it won't even get through. So it's not just synchronization, but it's reliability is the other reason we do that. But we're still well within the sort of like sub 100 microseconds arena. We're looking at 10 typically for VPNs over public internet. We generally see something like 30, 40 microseconds synchronization.
Excellent. So we've got about 1 minute left for each of you. So I'm going to give you a really unfair question. What's the impact of going into the cloud, where you lose a lot of control as soon as you get your first hop into your cloud provider?
Yeah, go for it. Go for it, Richard.
Okay, so I would say this is something we've suddenly had to go up the learning curve in the finance industry with over the last 18 months, and it's going well. What is clear is that the likes of AWS are very cagey about letting you actually treat the cloud as a real data center, when obviously it is, right down to even finding out where it is. So actually, it's quite, in financial services, it's been quite a boon for us because, you know, the practicality of installing clocks locally is just not there. And I think the same is going to happen in broadcast industry as that moves to the cloud. The possibilities for local sync are just going to be fewer and fewer.
Gerard?
Yeah, great question. I think if you kind of step back a bit and think about synchronization again, then why do we need the PTP and why do we synchronize? What are we sampling with the PTP? And it's the analog signals, right? It's the camera and it's the microphone. So what we need to be accurately timestamped is the stuff that is captured by an analog device that is providing signals into the production chain. Once you get into the cloud, you may want to use accurate time to limit the amount of buffering you need or to synchronize flows together. But do you need PTP accuracy? That's the question I've got for you, right? I don't think you need 2059 accuracy. It's certainly true that, I mean, what you need is enough accuracy that you can align stuff. Timestamps is important, but accurate timestamps created from an accurate clock are probably not important. So I think we all need to have a bit of a rethink about what production in the cloud means, because it doesn't mean the same as it means in a studio, in my opinion, because the cloud doesn't create content from a camera. That has come from a real camera, right?
Yep. Well, it sounds like we should be teeing up a next webinar on live production in the cloud. What do you really care about?
Yeah.
Excellent. Well, that brings us right to the top. 6 o'clock and 2 seconds. So we overran by 2 seconds. I'm sorry, Mark. My time wasn't using PTP here. Otherwise, we would have been more accurate.
I was going to say, is that the time? I better not. So thanks, Bruce, for leading that, and thanks to all of our speakers. It was a very, very interesting session, and thanks for your time for sharing your insights with us. That is great. So the RTS Thames Valley Technology Centre specialise in talks which matter to you. If you'd like to hear more interesting seminars, then please follow us on RTS Thames Valley from Twitter, or just Google RTS Thames Valley to stay up to date. Once again, thanks for joining, and I wish you all a very great and safe evening. Bye now.
Okay, thank you
very much, everyone.